Hi everyone, welcome back to Mutlu Learning Hub. In this video, we are going to talk about cross-validation and more importantly, why one train test split is often not enough. A lot of the time, we train a model, check one validation score, and move on. But the real question is, how much should we trust that score? That's where cross-validation comes in. It helps us understand not just performance, but also how stable that performance really is. Here is the plan for this video. First, we'll show why a single split can be misleading. Then we'll go through how cross-validation works. After that, we'll look at some common types of cross-validation and when to use them. And finally, we'll talk about what cross-validation actually gives us back and how to interpret it. Let's start with the main problem. One holdout split gives us only one view of model performance. And that can be a problem because the score depends on which data points happen to end up in the validation set. So even if the data set is exactly the same, a different split can give you a different result. And when the data set is not very large, that difference can be pretty noticeable. So in this picture, the data is the same each time. What changes is just which points are held out for validation. And once that changes, the validation score changes too. That's the key issue. A single split can make the model look better or worse just by chance. So what does cross-validation do instead? The core idea is simple. Instead of evaluating the model once, we evaluate it several times. We split the data into k folds, then we train on k minus 1 of them and validate on the remaining fold. For example, here we have 5 folds, and in the first run, one fold is used for validation and the others are used for training. This gives us one validation score, but we don't stop there. Now we repeat that process. Each fold gets one turn as the validation fold. So in run 1, the first fold is used for validation. In run 2, the second fold is used for validation, and so on, until every fold has played that role once. That means each data point appears in validation exactly one time. And an important practical detail here is that the cross-validation is usually done on the training portion of the data. The final test set should stay untouched until the very end. So instead of trusting one split, we rotate the validation fold and get a more reliable picture of performance. At this point, it's also important to say that cross-validation is not just one thing. There are different versions, and the right choice depends on the structure of your data. Different problems need different validation strategies. Here are common ones. First, standard k-fold cross-validation. This is the general purpose version. You split the data into k-folds, rotate the validation fold, and average the results. Second, stratified k-fold. This is especially useful for classification problems when the classes are imbalanced. The idea is to keep the class proportions roughly similar across folds. And third, leave one out cross-validation. In that setup, you train on almost the entire dataset and validate on just one observation at a time. That can be useful when the dataset is very small, although it can also be more computationally expensive. So the main point here is don't just pick a validation method automatically, match it to the problem. There are also situations where random folds are just the wrong choice. If observations are related to each other or if the data has a time order, then the fold design has to respect that structure. For example, in group K fold, all samples from the same group stay together. You do not want some of that group in training and some in validation, if that would leak information. And for time series, the rule is even more important. Train on the past, validate on the future. So in these settings, random splitting can accidentally give you overly optimistic results. So what do we actually get back from cross-validation? Not just one score, but a set of scores, and that matters. The mean of those scores tells us about average performance. The spread tells us how stable that performance is across different splits. So, if two models have similar average performance, but one of them varies a lot more from split to split, that model is usually harder to trust. That's why cross validation is not only about getting a better estimate of performance, it's also about understanding stability. Cross validation is especially useful when data is limited because you want to make the most of the data you have. It's also very useful when you are comparing models or tuning hyperparameters. And more generally, it helps when you want to know whether a result is stable or whether it depends too much on one lucky split. So instead of getting one estimate, you get a more reliable picture. That said, cross validation is not automatic. For time series, random faults break temporal order. If there is leakage in data, cross validation will not magically fix it. And if pre processing is done before splitting, then information can leak across faults. So things like scaling, imputation, feature selection, or any pre processing step that learns from the data should be done inside each fault, not before the split. This is really important. Cross validation is only useful when the whole evaluation setup is sound. I also want to connect this to regularization because these two ideas are related but in different ways. Regularization helps reduce variance in the model itself. Cross validation helps us measure variability in evaluation. So, one is helping control model behavior, and the other is helping us assess how stable our performance estimate is. Together, they help us choose models that are not just accurate but also more dependable. So, if you remember just one thing from this video, let it be this: one split gives you a score, cross validation tells you how much to trust it. Thanks for watching. If this helped, feel free to like, subscribe, and share the video with someone who is learning machine learning or model evaluation. See you in the next one.